Hello, everyone. I'm Julian Wong, architect at DataVisor, and this is my colleague and DataVisor CTO, Fang. Thank you for joining us in this talk about fraud fighting tools. So we'll be going over four main tools for fraud management in this webinar: reputation list, rules engines, supervised machine learning, and unsupervised analytics. As we talk about each of these four tools, we're also going to go from less complex to more technically complex. So I'll go over reputation lists, rules engines, and supervised machine learning, and Fang will talk about unsupervised analytics and algorithms. So I'll start by talking about reputation lists first. So what are they? Reputation lists are resources with information on an object's high-risk activity or good status. So for example, an anonymous proxy IP address that's used for spam, or a device ID fingerprint that is associated with a user marked as a fraudster in a large fraud ring. You can sort of think of reputation lists as blacklist and whitelist. In the case of an IP address blacklist, you can get a lot of information about it, such as the type of IP, is it an anonymous proxy or VPN, is it static or dynamic, and why was it blacklisted. For a phone number, you can get info on whether or not it's been used for automated calling, is it a landline, a mobile number, a voice over IP number, and who the telecom carrier is. And reputation lists are usually obtained from open public sources, also like third parties that specialize in certain types of items, or in-house through collecting your own data. And although they're very basic, reputation lists can be powerful. They can be used to stop bad actors while allowing good people or processes to go through your site. So we'll see a simple example coming up next. Reputation lists, they operate in a sort of really straightforward manner. So as an example, let's look at how it works for detecting email spam. So the email sender or IP or domain is checked against a blacklist in a database. And if there's a match, a decision is then made on whether or not to deliver the message to the receiver's inbox. So if the IP address is tagged as being on a spam block list, then the email is not delivered. And you can find many such lists online at, for example, like the Spam and Open Relay Blocking System, otherwise known as SORBS. And they've been providing DNS-based spam blocking for more than 20 years now. Also, sites like What Is My IP Address also have blacklist check that direct you to over 50 different DNS-based anti-spam lists. And the Spamhaus blacklist, which I'll just call it SBL for short, is a database of IP addresses from which Spamhaus does not recommend the acceptance of email. So the SBL is a real-time database of IP addresses of spam sources, including things like known spammers, spam gangs, spam operations, and spam support services. So whitelist are almost always built internally because each company has specific guidelines of what they may consider VIP users or entities. A primary benefit of reputation lists is that they're conceptually really simple to understand. Essentially, anything on the whitelist you allow, and anything on the blacklist you don't allow. So most organizations can benefit from utilizing reputation lists, and they should be considered as a first line of defense for fraud management. You know, reputation lists exist for a number of things which I've already mentioned, such things like email addresses, IP addresses, device ID fingerprints, credit card numbers, phone numbers, even people's names, such as on like an OFAC and SDN government list. And so while they're simple to use and easy to understand, they do have some limitations. I mean, IPs, emails, and credit cards, for example, can get out of date. So they will need to be constantly refreshed, downloaded, and updated. These lists are also ideal when you're dealing with fraud that you know, and the types of fraud you are encountering are low in terms of the number of attacks and types of fraud attacks that you see. You know, they are more effective when your business has lower risk and you're not prone to new types of fraud techniques. So while we'll be talking about machine learning and unsupervised analytics later, but reputation lists are also created and added to from predictive models today. You know, like blacklists are compiled using predictive models that analyze hundreds of variables for each sending IP address, for example. You know, the blacklist scores IP addresses in real time, and it also incorporates things like, you know, the volume of like the traffic activity, spam traps, and complaint sources. So we will start a module on rules engines now. In going from reputation lists to rules engines, you are going from mainly a data source to now applying logic on top of the data source to take some form of business action. I mean, rules engines are basically software that takes predetermined actions based off of certain criteria. They separate the business logic from the application code, making it nice for somebody who's like a fraud analyst to manage building rules themselves. So in this sort of image that you see here, it's like some form of event. You know, it could be like a sign up, a product sale, or insurance claim, is run through a rules engine, and the rules engine decides whether or not to take one of three different actions, either accept, reject, or maybe potentially escalate to a human for further review. There are three main ways that rules engines work. The system can go through the rules one by one, and if the rules engine determines that any rule is triggered, it will take the appropriate action and skip or bypass all the other rules. I mean, in this type of setup, you have to be really careful how the rules are ordered, because if you have a rule that is meant to detect bad behavior and it's nested below other rules that look for good behavior, the rules indicating good behavior would be triggered first, and a potentially bad event could be labeled as being good. You know, a very common case of this is when a rule that looks at the agent of an account is placed very early or first in the rule set. So a fraudulent account that has been sitting there incubating for a long time before springing to do harm would be accidentally approved. Now, rules engines can also employ weighted scoring mechanisms. For example, in this table that you see, each rule has a score value, you know, positive or negative, which can be assigned by an analyst or a domain expert on adding the rules. The points for all the rules triggered will be added together to compute an aggregate score. So rules for flagging fraudulent behavior or bad behavior have positive scores, and a rule for flagging, let's say, good behavior has negative scores. So subsequently, you can think of a rules engine as helping you establish business operation workflows based on the score thresholds. So a different score range can lead to different actions taking place. Scores higher than, for example, let's say 1,000 can have a different action than scores less than 0. And as I noted earlier, an order can be rejected, approved, or flagged for further review. In the third case, rules can be combined and logic can be applied sort of in an if-then type scenario. You know, for example, like if a user's email is from a free email service and they're posting comments very fast, you might flag them as a spammer and remove their ability to post content on their site. So rules engines rely on domain expertise from fraud analysts, and the applications for rules engines can be quite broad. You know, rules engines can be used to detect across a variety of fraud, from stolen credit card payments to fraudulent mobile game installs to fake user account registration and fake content generation. We will walk through the case of a user acquisition fraud in mobile gaming. So just bear in mind the simplicity of this example, as it's just meant for the purpose of illustration. So the user sees the game advertised on a web page. Then the user installs the game and plays the game for a short period of time. After this has happened, the rules engine runs and certain rules are triggered. Right? The game install happened too quickly because the time delay between when the game was the ad was viewed and the installation of the game was like less than 5 seconds. Also, based on the IP address, the country location where the game was installed is different from the country from where it was played. And also, there was no activity after 8 hours where the game was installed, and usually the vast majority of new players show activity weeks after the game installation. So all this could add up to indicating that the fraudulent ad publisher delivered fake traffic just to install the game to get the revenue share for the install. So for each of the different rules that were triggered, there's a different positive score indicating bad behavior. The scores are added, and if it exceeds a certain specified threshold, it could be considered fraud. So in this particular case, the game install is considered invalid and deemed fraudulent. So rules engines are ideal when you're dealing with fraud that you know, so that you can build rules around detecting it, and the number and types of fraud you're encountering are low. So your business's risk profile is such that you're just starting to see different types of fraud attacks, but they're still sort of like maybe fairly unsophisticated manner, and you have a good handle on what they are and what to look for. Okay, so moving from rules engines to supervised machine learning is sort of like graduating to like almost like another technical level. With rules engines, you have domain experts creating rules to tell the system what to look for. But in supervised machine learning, this is done more automatically by the machine algorithm. So what is supervised machine learning exactly? Well, it's basically like an algorithm that learns to perform a task from like known examples. And it's also one of the more advanced tools you have to do fraud detection. But also keep in mind, it's important to have good data to train the model accurately. So in supervised machine learning, we're given a data set and already know what our correct output should look like. And the idea is that there's a relationship between the input data and the output result. So supervised learning refers to the fact that you give the algorithm a data set in which the right answers were given. For example, let's take a look at a set of data for prices houses were sold for based on square footage. So you plot the prices versus square footage, and it looks something like this. Now let's suppose you have a friend that has a house that it's 600 square feet, and she would like to know how much she can sell it for. So how exactly can a supervised learning algorithm help here? Well, one of the things that it can do is sort of fit a straight line through the data. Sort of, and based on that linear model, it looks like it's about like $900,000 for that 600 square feet home. So maybe there's a better, but maybe there's like a better algorithm for doing this. Like for example, like a second order function, right? And using this algorithm, we see that maybe like it's actually about $1 million. So essentially what we did here is we gave the model a data set of houses in which for every example in this data set, we told it the price the house sold for, and the task of the algorithm was really to produce more of the right answers for the house price. So next, let's break supervised machine learning down into some of its main steps. Building machine learning models is an iterative process that involves a number of steps. I'll go through some of the major components. One of the first steps is understanding the problem you're aiming to solve and collecting the data set. In collecting the data, having someone who is a domain expert in the data can be handy to suggest fields that are most informative. And after the data is collected, it also needs to be processed, which can sort of include removing sample data rows that contain missing values or incorporating data that is relevant to solving your problem. The training data usually comes from manual reviews and decisions made by fraud analysts, for example, on whether or not a transaction is fraudulent. The next step is splitting the data into training data and validation data. The training data is used to train the algorithm of your model, and the validation data is used for tuning the parameters of the model. And after the data comes determining the attributes that sort of explains the patterns in the data. And this is like identifying the variables in the data which could be good at predicting an outcome, otherwise known as feature selection and extraction. So once you have the features, you can start applying a learning model, and examples of such algorithms for supervised machine learning include support vector machines, naive Bayes, decision trees, and logistic regression. And less attributes are also more desirable because it reduces the complexity of the model. And a simple model is much easier to understand and explain. So after you have the features and the classifying algorithm in place, you train the model with the training data set. The model is evaluated using validation data, and then fine-tuned if necessary. After training the model, the fitted model can be used to predict the outcome from like new sets of examples. Like as noted, the process is iterative, so you can also go back and forth between steps. With your model, you give it new data or test data, and there may be additional feature extraction that's done. Then the model detects new instances of fraud and essentially gives new cases labels of either good or bad. We can look at a set of data next just to see how one typical supervised machine learning algorithm works. So let's walk through this example right here. So suppose we have the following data set of transactions with outcomes, right? There are 12 cases total, with 8 being labeled as fraudulent transactions, colored in red, and 4 being valid transactions, colored in black. And we want to know whether or not a new transaction is fraud or not. So the features, email address type, IP address type, and linked accounts density are determined to be sort of good predictors of whether or not a transaction is fraudulent. So is the user using an email from a private corporation? Is it a free email from a free service, or is it from an email from a university? Is the IP address transparent and you can see the real IP address, or is it hidden and anonymous? So does the user have a high number of connected accounts or not? So this is our training data set, and this is the data that we'll be using to build a model. And the question is, a new set of data comes in, let's say case number 13, and this email is a corporate email, the IP address is transparent, and the linked accounts density is high. So the question is a transaction fraudulent or not? And there are numerous algorithms for supervised machine learning, and one modeling approach is a decision tree. And I'll use it to go over the previous data that we saw. So the decision tree tries to take each of these attributes and makes the best sort of inference, right? Assuming that the email is from a free service, is this transaction bad, and with what chance and what other factors may influence it? So let's look at how it operates. Suppose we take email address type as the first attribute. It could be a corporate email, and when it's a corporate email, these are the training examples that correspond to corporate email. One case is fraud, and the other is not. The email could also be from a free service, and when the email is from a free service, all transactions are fraud. This would be considered like a pure subset, meaning all positive examples or all negative examples, and there's no mix. And so when the email address belongs to a university, there is 1 fraud case and 3 good transactions. And the way the algorithm is going to proceed is it's going to break these sets down into all fraud or not, and aka a pure subset. So for the free email service, it's a pure subset. there's no need to further break down since each case is fraud. If it's a free email service, we know it's fraud. And when it's a corporate email, there's still a little bit of uncertainty. For corporate emails, it will look at another attribute, for instance, IP address. And splitting an IP address gives the type anonymous or transparent. When the IP address is anonymous, the transaction is fraud. And when it's transparent, it's actually good. So this particular path of the decision tree now has two pure subsets, and the algorithm would sort of stop. And now if you do this for the university emails, for university emails, it will now look at linked account density. Splitting on linked account density gives high and low density. And when it's high, the transaction is fraud. And when it's low, it's good. So again, this particular path of the decision tree now has two pure subsets, and the algorithm would stop. So like this point, you have taken your training data and essentially sorted it into pure subsets. And then once you've replaced the training examples with decisions, you get this decision tree. Now we have a model for sort of predicting when an order is fraudulent or not. So how does it predict for the new data? Well, the decision tree is like a logical formula, if you think about it, that tells you in what cases the transaction is fraudulent and what cases it's not. So the email address type is a free service. The order is fraud. If it's a private corporation email address and the IP address is anonymous, then the order is fraud. If it's a private corporation and the IP address is transparent, then the transaction is okay. And if it's a university email and has high linked account density, the transaction is fraud. If the email is from a university and the linked account density is low, then transaction is okay. So taking the new data, if we look at the decision tree, we go down the path of private corporate email, business email, because the email address is from a corporate domain. Then we look at the IP address because that's the next attribute in the branch. Since it's transparent, the transaction is good. So there you have it. And just one final comment about supervised machine learning. So supervised machine learning is ideal when you're dealing with fraud that you have good training data for them, and your risk profile is high, meaning your marketplace has achieved good liquidity in its market, and fraudsters see it as an opportunity to make gains. Fraudsters are attempting a variety of ways to game your business. Attacks can be mass-scale attacks with thousands of accounts. So at this point, I'm going to turn it over to Fang, who is an expert on big data analytics and fraud algorithms, to talk about unsupervised analytics.
Thank you, Julian. So unsupervised analytics, what is it? So Julian has explained the supervised analytics. It's actually different from supervised analytics. The main difference is that it does not require any training data. It automatically discovers and learns patterns from a huge amount of data without any prior knowledge of what to look for. There are two main categories of unsupervised algorithms that we will cover in this webinar. The first is clustering analysis. It identifies, on the high level, it identifies the similar users or events in a high-dimensional space. In the fraud space, because one attacker usually controls many different little accounts to conduct bad behaviors. So these bad accounts' behavior naturally clusters. That's why the clustering algorithm is able to identify them. For graph analysis, it's different. It looks at the connectivities among the users to identify suspicious connectivities. There are well-known algorithms such as the connected component, strongly connected component analysis, and the graph cuts that actually are able to identify suspicious graph subgraph components. So the main challenge of the problem is that each data point is actually a user. Before we get into the details, we look at the toy examples here. We have user signups. We have many new user signup. We do not know any history of these users, yet we want to determine whether these users are good or bad. Sounds pretty challenging. How do we do that? So for each user, we can extract 6 types of features in these toy examples. For example, what time they sign up, whether the name is capitalized, whether the IP address comes from data center or proxies, what the browser they use, what the OS they use, what's actually the timing behavior, when do they add a card, and what the time they purchase goods. And using clustering algorithms, we actually are able to cluster these into 3 main clusters and some sporadic users. So if you look at the two big cluster here, these are mostly look like normal users. They actually sign up accounts in 2 to 4 p.m.s and using Firefox, and then the add card to purchase time difference is 2 to 5 minutes. Here's another similar big good user cluster. On the left side, there is this very tight cluster actually appearing here. If you look at that, these are the users actually sign up accounts at 3 to 4 a.m. They use data center IP address, they use Chrome and the same Windows version, and their add card to purchase time difference is very little. It's less than 1 minute. If you see just one user having this weird behavior, it might be normal because someone may work late and want to do something in the middle of the night. But when we see a cluster of these users actually all having the same behavior, this is highly suspicious and likely to be a fraud set of users. This is the essence of the clustering. So to generalize from this toy example, what we do is actually we put each data point of this user or transaction as a data point in the high dimensional space. Each user can have thousands or hundreds of thousands of features. So the clustering algorithms actually cluster the data points into the different clusters and identify suspicious clusters. The challenge of this approach is that we need to determine the right number of clusters, and we also need to distinguish good cluster versus bad clusters. And most importantly, clustering algorithms work pretty well on small amount of data. When there are hundreds of millions of data points and a super high dimensional space, how to efficiently process this data to identify the suspicious cluster. For that, dimensionality reduction is actually the key. Let's move to another set of unsupervised algorithm, which is a graph analysis. We also start with a toy example here. So this is actually a set of normal users. We can see some of the users are actually loosely connected with each other. Some are closely connected with each other, for example, family members. When a bad one comes, a dummy attacker can actually try to send messages, spam messages to all these good users. It's very aggressive and it has very little response rate. So by looking at the alt degree of this attacker and their behavior from the graph, we can easily identify this guy as a spammer. But not all of the spammers are so dumb. Some of the smarter attackers, they actually form cliques among themselves. They send links to each other, they friend with each other, and they also send a low-rate attack to normal users. To detect this kind of a more stealthy group of attackers, we can run graph algorithms such as strongly connected component and also graph cut. So the challenge here is that when we have, again, we have a lot of users, and also we need to define the links between these users. The link among these users can be explicit. For example, a user A sent a message to user B, or they actually be explicit friendly of each other. But some of the links can be also implicit. For example, two users go attend the same event, they like the same post, etc. So how to efficiently represent the relationship among the users, and how to actually process this graphs, which has hundreds of millions of nodes, to identify the suspicious subgraph like this is a key for the graph-based analysis. Now we have looked at two toy examples. Next, we will show two real-world examples to see how this unsupervised-based approach can detect. So this is actually a real-world example of attackers in a social event. So the x-axis here is actually the time. The y-axis here is actually the number of users. You can see that attackers first incubate. They test among very small number of users in the beginning of the May. They say, oh, there is a loophole in the system I can go through. Then in June, it actually prepare a script to massively register user accounts. And for that, they only register users, and they haven't done much activities about these users. And they let these users stay. So we call them sleeper cells. And in 2 weeks later, in late June, they start doing doing actions on these sleeper accounts. They start to add location, add hobbies, signatures, and phone numbers, and then they connect with each other. And after that, they launch attack. This attack collectively redeemed 3,500 gifts. So if we look at this attack, the traditional approach is very hard to detect them, because if you look at the use blacklist approach, when this group of users are signed up and conduct activity, they actually use distributed botnets and cloud providers. So it's very hard to get these users are bad based on the IP address reputations. If you also use like rule-based systems, these users, when they attack, they're already 2 weeks old, and they have some good reputation. They haven't done very aggressive behavior in the beginning of the sign-up, and they have a perfect profile. If you look at each individual users, they look very normal. So the rule-based system is also very hard to detect these guys. And for machine learning-based approaches, because this attack is so new and they launch attack in a sudden behavior within a few days, it's very hard to collect labels and start training. By the time we train, they already shift behavior. So in this case, this one is actually a perfect example of what unsupervised attacks, because these unsupervised analytics can detect this because they have very strong coordinated behavior, and while the previous generation of a solution cannot. Let's go to another example of a transaction campaign. We show 3 user accounts here. The first 2 is one user, second is one user, and here is another user. If you look at them individually, they use different IP address, different names, different credit cards, and device IDs, and very different purchase amount. But if you look at them in a close way, they actually have very similar behavior. Each account have a very small testing amount of transaction to a US location first, and then they have a much bigger transaction to Philippines. That's their main target. If you look at it in a global way, you can see there's this group of users share a similar behavior, and they are highly coordinated. That's how the unsupervised algorithm can detect these guys. To summarize, the main advantage of unsupervised technique is that it does not require any training data. It can discover new form of fraud, and also it identify large scale of fraud rings. Because it identify group of bad users, it has very low false positive rates. It can identify attacks before it actually damage occurs. In our previous example, when the user actually registers with unsupervised based algorithm can detect it before it actually conduct bad malicious behaviors. The challenge is that we need to look at all the users together rather than individual users, and then the computation complexity is pretty high. Now we look at how DataVisor and supervised detection architecture works. A very familiar model for attack detection is using the supervised machine learning to output the individual bad account. We support that as well. But on top of that, we use Apache Spark to implement unsupervised campaign detection that detects malicious campaign from the raw data. The output of it can directly use for blocking attacks. In addition, it can also be used as labels to supervised machine learning techniques to identify sporadic bad users that are not tightly fit into the malicious campaigns. Both these modules actually run on top of Apache Spark on the distributed processing infrastructure that can process hundreds of millions of users and trillions of features. However, the Apache Spark does not support real-time computation. To support sub-second latency detection, we also build an in-memory real-world correlation module that interacts with the Apache Spark that supports very low latency computation requests. Hope that actually gives you some ideas of how unsupervised algorithm works and how our architecture is. There's also, I think in our presentation, one thing that we didn't cover is actually abnormality detection.
Sure.
Yeah, if you look at abnormality detection, it also kind of it can be arguably a unsupervised approach. The main idea is actually you look at the distribution of normal users and then look at the long tail of this normal user. If there are some user actually behave very, very differently for all the rest of the group, they are highly suspicious. It is actually a good way to detect bad users, but there are two drawbacks in that this approach. The first is that it does not detect the users actually pretend to be normal users. For example, in recent cases, we see attackers try to mimic normal user behavior very well. They, for example, in our example, they sign up at a good time and they do small amount of transaction first, etc. And the second is actually when you cut off the long tail of and think the users actually do not fall into the distribution of good user as bad, it has very high false positive rate. Like our example showed before, if only one user actually doing a transaction at the middle of night, 3 a.m., it is suspicious, but it may be actually someone actually working late. So by looking at that alone cannot be actually very strong indicate that this user is actually bad.
That's sort of going to be a pretty tough question to answer. I think a lot of it is, we've definitely seen that fraud has become a little more sophisticated. While I would definitely say, many years back, there were things that sort of like stuck out where you can say like, these are certain browser types or operating systems that that look sort of like fraudulent or could be most problematic. Like you see sort of like really bad traffic coming through them. It's a lot more different now. I mean, there's a lot of new technologies that users have access to. And like one example I'll just talk about is like things like, like phone emulators or like smartphone emulators where you can actually mimic various different types of devices just like on your mobile smartphone. So in that sense, some of the data that we actually see, I mean, it actually spans across a variety of different browser types and operating system types. I think to me, one of the ideal ways to really check for something like that is to sort of like benchmark it against if you can develop a profile of what you think your good users are and like, types of browsers and operating systems that they're using, and then sort of do a comparison against everything else. And you may be able to sort of like separate and see like there's some subtle differences between some of the fraudsters. For example, like a bad user for any given user session may exhibit, let's say, multiple different browser types and operating systems, whereas your typical good user might only have like one browser and operating system type that's sort of consistent throughout that particular session. But that's sort of like a very simple explanation of this.
Yeah, I want to add that some of the browsers actually they do pretty good job of mimicking the most popular browsers being used right now, the fraudster. But some of them are actually not so careful. We actually see a lot of them using, for example, scripted Apache scripting browsers, user agent. Those, when we see it, is obviously bad. Some of them also use very older version. For example, when we see the user acquisition fraud case, that some of them use actually very, very old phones. So a lot of them use like iPhone 2, iPhone 4, those like old phones, and a group of them. So these are also like signals because we need to keep track of what's the most popular ones. And sometimes the attackers, a funny case that we saw, that because they want to be in advance and be most popular, they even have the iPhone 8 UA, which is actually not available. I think they try to be advanced as well. But looking at the browsers and then the OS version, that you can build some telemetry out of that, what's popular now and what's actually malicious scripting ones. But again, these are just one signals that it cannot be used to detect alone because many attackers try to hide themselves really well. I think that's actually a very good question. I think one of the main challenges for clustering-based algorithm is actually how to differentiate the good cluster versus bad clusters. For users like old users, etc., you can see their behavior. But for flash crowd events, for example, there's sudden new ones that are coming up or some new events or news that we will see a fresh crowd of users, like for example, if people install a lot of Pokemon Go, those actually can be legitimate. And the key challenge of identifying this fresh of the crowd versus attack is actually looking at the behavior of these users, how these users are actually behaving, what they actually do after they sign up, etc. Because in normal users, if they have a flash or call at one time they have similar activities, because they are normal users, they have very different behaviors and they use different devices, they do different things afterwards. But for attackers, because they use a similar script, it's very, very hard for them to actually do randomization on all kinds of different features. So there are some dimension that we can actually still capture them out. Yeah, that's actually a great comment. I think feature selection is actually very critical for the clustering algorithm. In our case, we actually have this feature selection, but we also do not heavily select features, because many of the feature selections are based on the historical labels. If you know how this attack works, you can select the set of features that's actually best relevant. But when the attacker change patterns, the new features actually can identify these new attacks may not be selected. So we try to actually be generalized and includes all kinds of features as much as possible. And our kind of Spark-based systems able to accommodate thousands of tens of thousands, hundreds of thousands of features. Browser cookies are useful in identifying some of the attacks. For some of attacks, attackers are actually not so careful, so they actually share the common cookie, and sometimes they ship the cookie to remote locations, etc. But in many other cases, they actually are quite careful. They will use brand new cookies. If you say the brand new cookies is suspicious, but a lot of normal users are there. So again, I think browser cookie and browser ID, this kind of information is a good indicator, but we see modern attackers actually have ways to overcome these. I think this is unsupervised detection is actually quite new. As far as we know, that's something that we are pushing for. Historically, it's actually been very hard because, as we mentioned, clustering algorithms and graph-based algorithms are computationally very hard, and then also it doesn't scale very well. But recently, with the big data analytics platform, the advancement, for example, the Spark systems, the Hadoop systems, etc., we are actually able to leverage the most advanced technology in the distributed computation big data field to help us actually bring this kind of a more complex algorithm into the real world. So that's something that we are pushing for.
Yeah, and I think what I'll add to this question is, the analogy I gave sort of like earlier during the webinar is like when you think about something like supervised machine learning, where you sort of have training data and examples, you're sort of teaching an algorithm how to do something or like perform a task when you already sort of like know what potential outcomes you want to like look for. Whereas with unsupervised, it's much more of a challenge, given the fact that you're sort of trying to figure out like the unknown, and a lot of these things are sort of like very new, and as a result, it requires, I think, like a different level of algorithm and engineering intuition here that is has it's starting to sort of like pick up some kind of adoption, but it's still like sort of like in the really early infancy stages right now.
But we see it's actually pretty powerful. It's able to identify attack in different sectors. So we encourage everybody to try that.
All right. So thank you, everybody. We appreciate you joining us, and hopefully this was very helpful to you.